All right, hi, it's Miss McGarry. We're going to talk about Unit 7. This is Unit 7. Unit 7, Worksheet 3. So the first part talks about Ohm's law and goes over some graphs that are similar to what we saw in the simple circuit lab. So when it talks about ohmic resistors, what we're talking about is that there needs to be a direct proportionality between current and voltage. So what we're looking here is a constant slope, so that we can say that voltage equals current times a constant resistance. So A and B follow that. C does not, because we can see that the slope here is changing, which would mean that it has a lower resistance in the beginning and it has a higher resistance for higher currents. There are some things that act like this. It tends to be things that heat up as you add more current to them. All right, so the next part asks about potential difference. So we're going to use Ohm's law for this. So the voltage is equal to the current times resistance. And this is one where it helps to know what the slope is or the resistance. So let's look at resistor A. Resistor A, if I look at the slope or the resistance, I'm going to get, for every 10 volts, I have 2 amps flowing through it. So this is going to be 10 over 2 or 5 ohms. So in order to predict how much voltage I'm going to get, I'm going to do on here. So we have, this is our current, which is 1 amp. And I have 5 ohms. So this is going to be 5 volts. Resistance in ohms of resistor B. Again, for resistance, I'm looking for the slope. So if I look at resistor B, in order to do 5, so since I have this direct relationship, I'm going to just rearrange this. So I have the resistance is the voltage divided by the current. So with this, I have 5 volts. That gives me 2 amps. So this is going to be 2.5 ohms. All right, moving on to problem 2. So in problem 2, it says each cell in a battery provides a potential difference of 1.5 volts. So for this, we need to know that 1.5 volts is the symbol that looks like one cell of a battery. So I have a short line and a long line. So looking at each of these, in circuit A, I have 3 cells, so I have 4.5 volts. In B, I have 6 cells, so that's going to be 9 volts. And in C, I have these two in parallel to each other, so I have 4.5 volts on the left and 4.5 volts on the right. But this actually, in total, it only provides 4.5 volts. So C and A are going to act similar to each other. When it says how much you expect the voltage drop across each bulb, so for this one, we need to look at, so these are 3 identical bulbs. So in a series circuit, the way that this is going to work is that each bulb is going to get the same amount of voltage drop. So if I have 4.5 volts to divide up, the first one will get 1.5 volts, the second one will get 1.5 volts, the third one will get 1.5 volts. In circuit B, they're going to be divided up similarly, but I have a higher voltage battery. So I have 9 volts to divide up between 3. So I'm going to have 3 volts at each one. And for circuit C, this one, again, is like the first one. I have 4.5 volts that I'm adding up. This one, when you have 2 batteries that are in parallel to each other, it's like having the difference between a AA battery and a D cell battery. They have the same voltage, but one can provide more current. So at higher currents, the D cell batteries are going to act a little bit better. But for our purposes in this one, it's going to be the same as A. Each one is going to have 1.5 volts for it. All right, in problem 3, it's asking us to make some comparisons. So in A, it's asking about these 3 parts right here, A, B, and C. And these are all right before, in the middle of, and right after a light bulb. So it uses the word flow rate and here means current, because current is the flow of charge. So in terms of the flow rate at A, B, and C, these should all be equal to each other, because in a series circuit, one thing is that at each point, the current is going to be the same everywhere, and a filament in a light bulb is just a small wire. In our second circuit here, they're not going to be the same, so that's covered in part C. All right, at part B, how does the potential at A, B, and C compare to each other? So again, B is in the wire. A has to be, so imagine, let's say that I had a 10-volt battery here. Then light 1 would have half of that, so 5 volts. Light 2 would have the other half of that, so another 5 volts. So at A, it's going to be 10 volts. B, it's going to be a little bit in the middle. C, it's going to be the lowest at 5 volts. So in this one, A is the greatest, then B, and then C.
All right, so I'm going to continue with problem 3C. How do the flow rates in X, Y, and Z compare to each other? Well, what they don't tell you here is that R stands for round. So it is a round resistor, and L stands for long. And if you think about how those characteristics of resistors affect the resistance, then you'll be able to understand how the current flows a little bit better. So first of all, the current that comes out of the battery is going to be all of the current, all of the charges, so that's always going to be the greatest flow. And then once we break off into X and Y, we know that those charges are going to split. Now, we don't know how they're going to split because we need to think about the resistors that are in each branch. So first of all, the round resistor is going to have the most flow because it is more open, if you think about round, versus a long resistor, which is going to take a lot longer for those charges to flow through, so it's going to have more resistance. And if we think about the inverse quality of current and resistance, then we know that a round resistor with with low resistance will have high current, so Y is going to come next. And then the Z current that flows through a long resistor is going to have high resistance and therefore much lower current. So it's going to be X greatest, Z the least, and it's based on the type of resistors that are there. How does the potential at X, Y, and Z compare for each other? And explain, well, these are parallel circuits, which means that the potential drop between each circuit is going to be the same. And potential drop basically means, or potential difference basically means the voltage. And so X Y and Z are going to have all the same potential difference. In the current below, all the bulbs have identical resistance. What is the voltage drop across each bulb? And sketch the charge density in each of the wires. So here we've got two batteries here of 1.5, so that's 3 volts. The voltage drop across each bulb is going to be, well, A is going to have the full 3-volt drop. B and C, assuming that they are the same, is going to divide the same resistance, is going to divide the 3-volt drop between them, so it's going to be 1.5 volts between those two. All right, so in number 5, we're talking about the flow rate through A compared to B, and then we're looking at the brightness. So the flow rate here, as you come out of the battery, it's going to be the total current, but as it hits this junction, as it approaches resistor A and B, the current is dependent upon the total resistance. Now, assuming that these resistors are the same, let's say A is a value R, because the branch with B in it is in series with another resistor C, we have to think about the total resistance in that branch, which would be double the resistance. In series, you always just add the resistors together, which is 2 times R. Now, the fact that it is double the resistance, the higher resistance, the lower the current, they're inverses, so therefore the current is going to be half of what it was for A. Now, if we think about it, let's say the current here is I, then the current would be half. So when we're trying to compare A and B, the current through A is obviously going to be greater than the current through B. In fact, it's going to be double. This is double. But that helps us answer the question about brightness. Brightness is related to power, and power is equal to current times voltage. Well, if we look at the current through A, the current through A has a current of I. Let's say that's our variable for current. And we have a voltage of 3V, which I'm just going to call V, and we're going to do proportions for this. If I'm comparing that to the current through B, the current through B we established is half the current of A, and the voltage is 1.5, which is half the voltage of A. And so if we're trying to compare how many times, the brightness is going to be a quarter of the brightness for A, and brightness is directly related to power. All right, so what we're going to do here is we're going to start working with series and parallel circuits. And what I like to do when I'm working with series and parallel circuits is to always have a vertical circuit that represents my series here. So I start with 3 volts, I work my way down, I have 2 resistors in a row, and then back to the negative side of the battery. I'm going to start here at the positive side, work my way around. So before I hit my first resistor, I hit position B. My 12 ohm resistor, I'll call that resistor 1. I have in between C and then my 6 ohm resistor, that's resistor 2. And then right after the 6 ohm resistor, I have position D and then position A. So this is D and that's A. Okay, what I like about parallel circuits, or sorry, vertical circuits, is that they make it very clear that the current is going to stay the same because it is traveling through one wire all the way down. And it also gives me a good visual of voltage drops as it breaks that vertical height, which I like to think of voltage drops as like gravitational potential energy. Every time it drops through a resistor, that's the amount of voltage that it is dropping. So you can see that the voltage drop is broken down between 2 resistors. The next thing I like to do, and I'm going to do this small because I need space for my other one, is to draw a VIR chart. So VIR at the top. I'm going to put my resistors in here, 1, 2, and then my total down here. And then I'm going to fill in the information that I have. My total voltage is 3. My resistors, for 1, are 12 and 6. And I don't know the current, but I can solve one thing. I know that in series, resistors add up. So I get a total resistance of 18. And then to get my total current, I would take my total voltage of 3 volts and my total resistance of 18, and I would solve for the current. Now, another trick I like to use is the VIR triangle, where you can use the cover-up method. Since I'm solving for current, I just take my my 3 volts and my 18 resistance, and I get 1/6. And let me just calculate that. I think it's 0.16. 0.1, I'm going to round it up to 0.17. So that's going to be the current that is traveling through 0.17 amps all the way across the circuit or through the circuit, and it's not going to change because, as we know, series has only one wire for the current to travel through. So 0.17, 0.17, and then from there we can multiply that by each resistance, because to solve for voltage, it's current times resistance, and then we'll get our answer. Now, I know that I rounded it to 0.17, but in actuality, this value is 1/6, and I will use 1/6 just because if I multiply 1/6 by 12, I know that's a nice whole number too, and it gives me nice whole numbers rather than decimals if I use the fraction. And then 1/6 times 6 is 1. So now I've got my voltage to answer all of these questions. And let's go back to A. It says, what's the voltage drop between A and B? Well, it's hard to tell from the vertical circuit, but if you go from A all the way around to B, the total voltage drop is going to be the full 3 volts. From B to C, it's the voltage drop for the for the first resistor, and this first resistor we already wrote here has a voltage drop of 2. Between C and D, that's our second resistor. The second resistor has a voltage drop of 1 volt. Calculated that with our current VIR chart, it's 0.17 amps. And then the power dissipated by each resistor, well, power is equal to current times voltage. And if I'm looking at the resistor, for resistor 1, I'm going to take my current, which is 1/6. I'm going to multiply it by my voltage 2, and that's going to give me 1/3. My power for the second resistor is a current of 1/6 again, but this time a voltage of 1, and I get 1/6. And remember, our units for power is watts. Now we're going to do the same process, but we're going to do it with a parallel circuit. And I'm going to I'll use a different color and squeeze this in here. But a parallel circuit starts with 3 volts, and it splits up into 2 branches. So that lets you know that your current is also going to be split up. I've got 12 ohms and 6 ohms, and I'm going to do a VIR chart for this one as well. So VIR, 1, 2, and total. Now, the thing about parallel circuits is the voltage drop here is going to be 3 volts, because when they're in parallel, the voltage drop is from top to bottom, which is a full 3 volts. So I'm going to write 3 volts for my voltage drop, and obviously that's my total voltage as well. I'm going to write in my resistance for 12 for resistance 1 and 6 for resistance 2. And then from there, I can use my cover-up method and know that current, based on my triangle, is equal to voltage divided by resistance. So then I'm going to take 3 divided by 12 and get 1/4. 3 divided by 6 and get 1/2. And then the current total is going to be, if this side has a current of 1/2 and 1/2 amps, and this side has a current of 1/4 amps. The total current that we get when they come together in the branch at the end is going to be the total current in and the total current out. And so 1/4 plus 1/2 is equal to 3/4. 3/4 amps. And then to get the resistance, I'm going to have my velocity divided by current, which is 3 divided by 3/4. And if I multiply by the reciprocal, it's 3 times 4/3, and I end up with 4 as my resistance. Now, there's another way of finding this resistance, and I'm going to go through those steps with you when we get there. And we're just going to check and see if that's our answer. Actually, it's the first question here. It says, determine the equivalent resistance of the circuit. Well, we did it using the VIR chart, but you can't always use the VIR chart to get the total resistance. So you always want to know your total resistance by equation by taking the inverse of all of your resistance values, so 1/12 and 1/6, and add them all together. And then once you get your answer, you're going to take the inverse of that. So 1/12 plus 1/6 is going to give me 3/12. And then to get the total, notice how this is 1/RT. I'm going to have to take the inverse of 3/12, which is 12/3. Actually, I'm doing that wrong. The inverse of our total is not 1/12/3, but it's just 12/3, which then gives me a total of 4 ohms. And that's exactly what we got here. So 2 methods. You definitely want to memorize this formula because the VIR chart isn't always going to give it to you. And then what's the voltage drop between A, B, and C, D? Well, that's easy because it's the same. It's going to be the total amount of voltage in our battery, 3 volts. The next question, what is the current in the wire leading from the battery to point A? So here's the battery, here's point A. So it's right at this junction. And we want the current leading from that battery to point A, which is the total current. And we already established that total current is 3/4 of an amp. And how much power is dissipated by each resistor? We're going to use our IR equation. So for not A, but 1, P1, we've got our voltage, which is 3, times our current, which is 1/4. So I've got 3/4 watts. The power through resistor 2 is 3/2 of a watt. And that is your final answer, P equals IV.